Here we have something not glimpsed upon normally by mere mortals. This is a collage of engine parts making up an engine, 356 engine exploded view, and all these parts have failed in horrible, miserable ways. If we can zoom in on the cam gear in the center, you can see that most of the teeth are missing the cam gear at the center. And then if we move it on up the crankshaft, you can see the broken two-piece Porsche crankshaft. It's actually a 912 crankshaft, broken in half through the thickest part of the flange. We go a little further back, and we can see a flywheel. Zoom it all the way in. Thank you. That has sheared off dowel pins on it, and the broken bolt that caused all this. We zoom out now. We'll do it slowly so you won't get seasick. We'll find a very interesting case first. Zoom into the case. See all that red RTV, that red stuff? It's not rust. That's called RTV, for room temperature vulcanizing silicone rubber. It's a silicone rubber used of choice by the turkeys. Comes in two flavors, red and blue. You see it on a case like this, watch out, lots of other problems occurred. We zoom out so we can see the effect of this particular problem. Stopping right there, we can see the big hole in the case. That big hole in the case was caused when the guy put too much RTV on it. The RTV came out in little dingleberries. The dingleberries got in oil passageways. They blocked up the passageways inside the crankshaft of the rod bearing. They ended up starving the rod for oil. The rod spun, overheated, and threw itself through the case. Not only that case, half, but of course, over on this side, the other case half. First one the maestro has seen that has a double header. Both halves of the case get destroyed by one rod. Usually it's one rod destroys 1/4 of the case, either top or bottom, whatever, but not the other half. But this time it got both. So now let's go back to the crankshaft area, and you'll see an interesting connecting rod there. That rod is bent in a rather interesting manner. Its right angle bend on the small end was caused, amazingly enough, by an improperly installed valve guide. How, you ask, can a valve guide do that? Well, in a chain of events leading to a meltdown of Chernobyl, or the chain of events leading to this, a very similar chain of events. Everything that could possibly go wrong did. And the same thing happened here. The valve guides, to install the valve guides in the head, you need to heat the head up so the hole in the head expands, giving the valve guide more of a chance to get into its press fit. So as you push it in, it also is helpful to lubricate it with certain lubricants to allow it to fit into place properly, and when the head cools down and stays in place, blah, blah, blah. If, however, you don't heat the head up first and try and force the valve guide into the unheated head, it'll go in, but it'll actually crack the valve guide boss around the cylinder head. And when it does that, you'll find that the valve guide boss may come inside the head. And when the valve guide boss comes inside the head, you will find that sometimes the piston will hit the head, and munch in the pieces of the valve guide, and then half the valve seat. If you look at that intake valve seat, you'll see half of it is missing. And half of that seat ended up being also pounded between the piston and the head, as half the intake seat popped out. And then with all these pieces bouncing around inside, the piston failed. And all the failed pieces in the piston joined in the cacophony and destroyed the connecting rod, eventually forcing part of the rod to go through part of the case. We'll go back to the rod. There he is. And that's the story on this rod. Each one of these parts has a story to tell behind it, why it did that. And this is but one of the many stories in the collection of parts. We expand out a little bit so you can see this particular connecting rod in all its glory. And move that crank away from it a little bit. We'll get to him later. So just move it this towards you a little bit. That's fine. That's good. Okay. Anyhow, this connecting rod, as you note, is split down the middle. And the cause of this is even more interesting. If you zoom in on a connecting rod, as far as you can go, you'll find they have oiling holes for the small end. And those oiling holes are either kind of two on the sides and two on opposite sides, or possibly three, usually symmetrically arranged. And every now and then you find a rod that has an oil hole drilled through the beam into the small end. The guy that did this to this rod thought, well, if there's one hole there, then I'll add a second. It must be better than just one. It provides better oiling to number 3 rod bearing, or wrist pin bushing and piston. And lo and behold, he did that very thing. He drilled the second oil hole, arrow-shaped oil hole. And the two met in the middle and formed a perfect stress riser, an arrow-shaped stress riser with no fatigue life whatsoever. And the crack started immediately and walked all the way down the big end, all the way down to the big end through the middle. There's a little crack on the side, midway on the side. That one was caused by actually another crack going through the rod, started at a stress riser that was the 1 in the part number of the connecting rod, forged in the connecting rod. It started right there. And by the time the big one got to the big end, the little one got through the side, and there was only this little piece left to hold the thing together when the big one finally split it. And that tore off just from exceeding yield strength. And of course, the rod went through the case. But the cause was a guy drilling a second oil hole inside that small end, thinking if some is good, more is better, and too much is just enough. Then we have the classical thrown rod, where there's not much left of it. The rod is broken in 3 pieces here, the middle section gone. In one case, this is the end cap, the cap end of a late model 912 rod here, right there, that was straightened out and then twisted 90 degrees. And you try and do that with a sledgehammer in less than about 10 minutes. This probably happened in a fraction of a second. We zoom out a little bit now. We get to the 4th one. This one is caused, along with a bunch of others I've got, called the gasoline hammer effect. This is when you come back to your car. It's been parked on a hill facing upwards. You have a leaky needle valve in your Zenith carburetors, and the gasoline is dripped into your intake manifold or through the open valve into the cylinder now. And you go to start it, and you hit the key. The starter goes, rah, rah, it won't go any further. You try a couple more times. You go click, that's it. So I figure, this is interesting, but you're very smart. And you're parked on a hill facing uphill. So what you do is you turn the key to on, put the clutch down, put the car in reverse, and back it down the hill, let it coast down the hill, and then you pop at the clutch. In which case, you have the classical gasoline hammer effect, or water hammer effect, and something has to give, and it happens to be this connecting rod piece here that bends. The crank doesn't break. Sometimes the piston does actually crack, or the cylinder does split, but in this case, the rod bent, and there's a 912 rod that has the very same effect with an almost equally bad bend. That's the weakest link in the engine. Okay, if we zoom out here. All right, as an aside, here is the pseudo fan is made up at the center by a Porsche camshaft, and the reason why you don't want to put that magic wand from the car wash down your oil breather can inlet and rest it there to clean out the inside of the can. The caustic soap goes down inside the case. You can actually see the water level or the caustic soap level in the case by the horizontal line around the bottom of the camshaft, with all the gear teeth, of course, corroded off on the area that was submerged in the caustic cleaner. Around this pseudo fan is 5 European heater muffler support girdles. And what's interesting about them is that all of them are cracked, and all of them are cracked. We can zoom in as far as possible. All of them are cracked the same way. They normally have 2 of those holes where the nut goes through, but you see the left-hand one is completely missing. And that crack will be identical to any other crack. There's another one. And the way they fail is exactly the same. The factory had a neat fix for it and almost worked. But they still crack like this, and the European heater systems need this girdle support for their muffler, or they lose their muffler. All right, moving right along here, let's check out what happens to bearings. Here's my favorite main bearing. This main bearing came out of an engine, a C engine, that was driving through Los Angeles when suddenly the crankshaft broke in half, back by the flywheel main too, and the guy knew that, but he was in a fairly, shall we say, bad section of town and didn't want to stop by the side of the road and get killed, so he kept driving as far as he could, and he ended up getting back to his driveway. And when I tore this engine apart, the flywheel thrust surface of the main bearing had been extruded to approximately 10 times its length and naturally about 1/10 its width, and extruded out in the form of almost a flying saucer. Some metallurgists from Lockheed have said this is clearly impossible, this cannot have happened, but of course here it is. At the same time, the dowel pin was plowing a furrow through the main bearing, plowing metal into the oil distribution groove, blocking said oil distribution groove. It got almost all the way around the bearing until about a millimeter or so from closing out the last oil passageway. The guy made it in his driveway and turned the engine off. Like I said, there's a lot of stories here. We go back a little bit here. This is a brass flywheel main bearing, homemade, and a good job too. If the tail has it true, at the machine shop at EBR2 in Idaho, Experimental Breeder Reactor 2, to fit like a 1953 two-piece case Porsche engine used in a VW bus. You've got that. This is made of brass, and the thing actually worked. It, very good job. The camshaft there, you know, with teeth on one side and no teeth on the other side, is of course something that you don't want to have in your engine. If we back that a little further, we see the typical, oh, yes, the atypical cam problem. We should make this a quiz. Should be able to see that well enough as to what is wrong with this cam gear. The maximum number of things wrong with this cam gear. If we can get the closest possible zoom on it. Yeah, what is wrong with this cam gear? There are about 5 things. Take a close look at that cam gear, and not counting the stuff in the middle, leaving out the stuff in the middle of it. We know it's worn and been welded improperly and poorly, but leaving that out for the moment, what other things are wrong with this cam and cam gear combination? We'll let you think about that for a while as we zoom out. And our next port of call here will be, of course, why you don't want to drop screws and nuts down your engine into your camshaft, cam gear, because sometimes the screws and nuts will take gear teeth off, and that's not a good thing to have floating around inside. And another reason, of course, for cam problems is, keep zooming out, is that they may not be one piece anymore. They may be 3 pieces. Or parts of them may be pieces, 2 or 3 pieces. These are the horrible cast iron normal cam followers. Zoom in as far as you can there, that always fail by breaking off their heads. And when they break off their heads, depending on how you've lived your life or how lucky or unlucky you are, if you're lucky or lived a good life, the head end will only go down in the sump and nothing bad will happen. If you've been a bad boy, the head end will be popped up as the cam lobe pops it up in the air. It gets whacked by the camshaft, and which hits a home run by driving it right through the cylinder wall, at the base of the cylinder wall area, destroying the case and the engine. So if you have a normal cast iron cam follower, it's a good idea to replace them before they lose their heads. Otherwise, you can have a Mickey Mouse engine failure. M-I-C-K-E-Y-M-O-U-S-E. There are, let's see, we have some examples over here. There's another broken cam follower. There's a cam follower seized in its bore from a thrown rod. There's a broken A cam follower. The A cam follower heads have no numbers on the inside of them, and they are quite thick. They're almost a 1/4 inch thick. But they break their heads off and it can be a disaster. This one here, this cam follower here, is an aftermarket one. The 2-ringer masquerading as a good cam follower when in fact it's a horrible cam follower. This, of course, is part of the reason why you have cam gears that have funny marks in them. Your screw-on cap, be it a C or 912, can come apart with rust and all the pieces fall down inside the camshaft. Okay, here we have the contest of the week. This cam gear has several things wrong with it, not counting the gorp in the middle. Ignoring the middle of that cut groove in the middle, the bad weld job and everything else, but there are about 5 things wrong with this camshaft cam gear combination. If you're very, 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 very smart, you can figure it out. The first time I saw this cam, it came in off of an engine that had been together and running for about, a few miles, and something happened to it. And the previous owner had taken it apart again and attempted to fix it, but the second time through, the engine would not start at all. He gave up in frustration, sold the engine. The new customer came in with this, and he gave it to me, and I found a few things wrong with it. It wasn't until 2 weeks later, though, the second cam gear came in. It has a couple of other interesting little defects in it, like 3 of them. But it was a Rosetta Stone for the solution to the problem of the first one. And when I saw this one at first, I immediately thought of the second one, because the second one only happened 2 weeks before. These things come in pairs sometimes. I was able to ask the customer that came in a critical question. And what was that question? Okay, this is a typically cracked crankshaft. This crankshaft is almost cracked all the way through. In fact, it probably would have failed another 5 or 10 miles, maybe, had it not been removed from the engine at the time and the huge crack saw seen. And where it cracks is always insidious. It's from the journal radius, so the rod bearing journal. In this case, the first rod bearing out from the flywheel, the usual spot where they cracked all the way through the thickest, fattest part of the flange. Just a little sliver is left, and I take this one to swap meets, and I drop it on the floor from a height of about 5 feet. And as you see, it's starting to separate, so only about 2 or 3 more drops may do it before it finally breaks. This is a classical crack propagation failure, and we're going to show you another one here in a second, a true classical crack propagation failure, maybe even be able to see the gyrations, the striations in it. Hang on. Okay, now this is a typical cracked crankshaft cracked in an atypical place. It's backed by the pulley end, but it gives you the idea that if you look at the striations there in that cracked section, you'll see that they form kind of a clamshell effect. And that's called a classical clamshell crack propagation. The crack started from the right-hand side of that journal radius there, and then cracked all the way through that big, thick part of the flange. It'll do it on any type of flange you want to make. It'll crack through in usually about 6,000 to 10,000 miles. Usually cause a bad crank grind, where the radius on a Porsche crank is that which is on the grinding wheel at the time the crank is ground. And the radius not be right on the wheel, it won't be right on the crankshaft. Many, many grinders aren't aware of that fact or don't care, and they grind the Porsche cranks with a notch for radius. The thing cracks very quickly, usually just outside the warranty of the shop that did it. But anyhow, that's a great example of a cracked crank. We have the rods cracked the same way. You can see the same crack propagation on the connecting rods, too. Now, going over here for the moment, we have some interesting oil pressure release springs. One, the two-piece one, produced like 0 oil pressure, and the second one was a Volkswagen modification. VW guy thought he had the trick hot setup, so he put in a very, very, very strong spring that suffered coil bind after compressing about a ½ an inch only. And that caused 200 psi oil pressure. Now, in a regular engine, where do you think 200 psi oil pressure might be dangerous? Another question for you to ponder as we continue this discussion here of the broken parts. Here we see an interesting one. This is a homemade cylinder air deflector. Clearly to replace one that had been missing, the guy made one up. But he forgot on which side of the air deflector to make the hole for the acorn nut. So he made it in the wrong place, so he had to make a second one. That's why there are 2 holes for the acorn nuts there. That hole on the far side is where you used a piece of wire to wire it around the pushrod tube. A homemade air deflector. We have more examples of them. In fact, we have a homemade side horizontal tin for a 912 here, all homemade. Actually done a bad job considering the primitive conditions out in the countryside. Continuing on, we have now a failed 912 piston with a rather interesting hole in the side. These guys fail from breaking their rings, and then the rings pieces bounce back and forth, eventually chunk the top of the piston, and then you're supposed to stop. If you don't stop and keep driving it, it'll eventually form a hole through the side of the piston, and like a Saturn V exhaust gas, the exhaust gases coming out of the engine are very hot, and they melt the piston, and all the stuff that used to be there in the piston is now throughout your engine and your bearings because it's aluminum. And the filter system is a bypass filter, and the magnet does not take out the aluminum pieces, so all that piston stuff there is now in your rod bearings. Congratulations, you lose. Over here we have a failed big bore kit piston. They fail not from the rings breaking so much as the ring lands. The area between the rings is failing. And when the first one goes, it starts to smoke a little bit, but when the second ring land goes, you end up with an oil passageway, actually a tunnel, between the combustion chamber, past the broken ring lands, and into the oil return holes of the piston. And again, the hot exhaust gas channels through there and melts the piston, fries the piston, and all the pieces go down throughout your engine because you don't have a full flow oil filter, blah, 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 blah. And let's see, over here we have a That was a failed big bore kit piston cylinder. We also have failed original cylinders too. That's kind of rare. And the valve train now. Here we have a broken exhaust rocker, a rather shrunk spring due to a fire, a valve, of course, seized inside its guide, a valve with a broken head, pretty rare in a 356, but it happens all the time on VWs. And we have another valve seized inside its guide, the broken valve spring, the broken intake rocker, and the life failures for them. The banana peeled guide, where the guide is loose in the head from improper installation, works its way free and goes around the tulip part of the valve and starts to machine pieces like taking off the skin from a banana. Eventually the pieces break off and fall inside, and we have some that are highly polished to the equivalent of almost jewelry from bouncing around, being hit by the intake valve and not getting through the chamber. Until finally the pieces do get through the chamber, and you hear knock, 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 and eventually the whole guide will suck through, and when that happens, you'll have a big hole in the head, will suck oil droplets like you won't believe, and your engine becomes a 40 horsepower smudge pot, able to block out the view of any Enterprise behind you, all three of them. Space shuttle, aircraft carrier, or Star Trek. My favorite exhaust valve. We'd have the assistant grab the end of the valve and rotate it very slowly, and it's in place without moving it. Now the valve. A really bent one. No, this way more. The first valve. Keep going. No, they were very warm before on the rocker. There, more, no, keep that, too far, that's it. Rotate it very slowly. Put its head on the paper. That's it, there you go, beautiful. Oh, that's a way to see, okay. Yeah, just leave it like that. You can get the idea. That's supposed to be straight. It's not straight. Still balances, though. This could be in a movie sometime. This is worth. I'll take bids starting at $100,000 for this valve. Okay, that was caused by using a B valve in the C head with the wrong keeper retainers. It came loose. The valve hit the piston, of course, and did that. The piston was rather unscathed, but the valve certainly wasn't. Here we have why you don't want to lighten your intake rockers by drilling holes in them. In critical locations, they end up bending on you during a race, and you, of course, lose the race because of that. And then even the factory makes mistakes. This is the magnesium rocker stand, the first attempt of the rocker stand for the Supers and Super 90s originally. They pull the studs a lot and end up having a serious problem with pulled studs. The stud design is not very good anyhow. The later aluminum ones are much better. If you have magnesium rocker stand, replace them with aluminum. You'll thank me for it. And over here we have another head and reason why. You don't want to take your Porsche engine to a machine shop that doesn't really know what they're doing. If the assistant would grab that part of the head, you'll see that has a removable head. If you'll hold that part up to the camera, a little further down, a little further up, to the left, almost a little further, right there. Right there. You see the valve guide, they tried a little up a little bit more. Up. There you go. See the valve guide, they attempted to remove with a chatter gun. Up. The chatter gun, on a cold head, as you try and force the guide out, the guide gets bigger as you drive against it, and it grabs the hole more, and eventually it grabbed the hole so well it wasn't going to budge, and the head broke off right there. Okay, that's a 69 912 head. You can tell that. All right, assistant, you can put it back down again. Get out of the way now. That's it. You can tell a 69 912 head by these little casting bosses. They're undrilled. The 68s do have them drilled for the air injection, and there's two of them, one per cylinder. And that's a 69 912 head. The 68 912 head has these same casting bosses, but they're drilled for the dreaded air injection, where they inject cold air into the hot head to meet the smog regs of 68. Big mistake. Almost every 68 912 head is badly cracked now. The other heads, all other heads, have fins there instead of casting bosses. And they do run a little cooler with fins there rather than casting bosses, so the earlier heads tend to crack less than either the 68 or 69 912 heads. But that's how you tell the difference. And now, wandering down to the fuel. Here we go. Now, these two guys are the oil pump gears. And the fact that they're oil pump drive gears, both have broken off tangs. The one on the right had a rather interesting experience. It was a hot rod engine. with a full flow filter. In fact, it was the man from Reno's engine, from the man from Reno's engine. And he had a minor problem with it one day. He was, the car had rolled down the driveway or something and smashed a tree, and he was taking the car to be fixed. They're driving it up on the trailer, and they fire the engine up, and no oil pressure. The light stays on. So they get back down, they check it out, and still no oil pressure. They take off the oil line of the filter, and they crank it over, and nothing comes out. So they say, so they fire it up anyhow and try to drive it on the trailer, and the engine seizes before it gets up on the trailer. So they have to push it on the trailer. Well, eventually got mad and put another engine back in it and sold me this race engine. So when they took it apart, what did they find when they get to the oil pump here? They found the tang broken off. And what did they find inside the tang? That little circular aluminum piece there inside the oil pump area. And what was that? They had put a full flow filter on this system. And when you put a full flow of filters on it, you have to block an oil line to prevent the filter from being a bypass filter. And they blocked this oil line with this aluminum plug. But it didn't put it in too well, and it came out and got in the gear teeth and bounced around a little bit. It was pretty chewed up. As it was bouncing around, a piece of it got chewed off and went through the now open passageway that was previously blocking, but is no longer blocking as it came out. That oil passageway bypassed the filter, went direct to the main bearings. That piece of chunk from this particular little disc here ended up on the flywheel main, seizing the engine before any serious damage could be done to it from the lack of oil pressure. So the rest of the engine was perfect. The bearing was shot, but that was it. Crank was fine, rods were fine, heads were fine, pistons were fine, everything else is fine. This was the only problem with the engine. And the reason why I maybe want to think about full flow filters or not put the plugs in that way. It doesn't work too well sometimes. Okay, now here we have a rather dramatic oil cooler. Well, not failure, but potential failure. The end plenum of this oil cooler, as you can see, experienced tremendous pressure internally. The question for the day is, how much internal pressure did this guy experience? I test him at 125 pounds per square inch of air pressure for leaks on an Adapto. And this guy must have had several hundred pounds, maybe 1,000 psi to do this. So we will entertain estimates on what, in fact, how much pressure it took to do this on this oil cooler. By the way, it was not leaking. Okay, returning now to this one here. We'll zoom in on him. Okay, so assistant, you can put that oil cooler down. This is a number 4 main bearing done by a gentle soul, who, as you can see, twisted, almost bent off the dowel pin end of the bolt that holds the number 4 main bearing in place. If you look at the number 4 main bearing, you can certainly see the gouge form where the guy missed the dowel pin hole and reamed its new dowel pin hole through the number 4 main bearing. If you look at the inside of the bearing, you see all the score marks and where it got all deformed and crankshaft machined it away and all kinds of bad things happened. This particular guy must be a real hip with the women, because if it doesn't go in, he forces it more. Here we have, of course, the symbol of this particular tape. M-I-C-K-E-Y-M-O-U-S-E. This is caused by attempting to probably hold the pulley from turning while you took off the nut by using a screwdriver in there, or maybe an attempt to pull it off somehow, but they broke the pulley here. I don't know how they did that, but it's amazing what turkeys can do sometimes. And here's another instance of that. First, let's take the shims. The one on the left, of course, is a homemade shim, and not a very good one at that, matter of fact, but that's a homemade shim. The one on the right is a factory-made shim with a factory boo-boo, where they were too close to the edge of the material, and they did it anyway, and there's a cutout there. But they shipped it anyhow. And now we come to the real goodies here. These are, in particular, the one on top, with all that red RTV all over it, and the funny stuff wrapped around it, is a great example of how not to do an engine overhaul. That red RTV, that red room temperature vulcanizing silicone sealer, so popular amongst the some trades, was gooped on in excessive quantities throughout everything on the stupid engine. This is the one that sucked the valve guide, valve guide boss from having improperly installed valve guides and then blew the engine that way with a crazily bent rod. Note this, even with all the RTV, it still leaks, so we had to put some type of muffler goop on it and wire it on with wires. And it still leaked, so I didn't succeed in solving any problem. Here we have a few rather bent push rods. That's a fairly common problem. And we already been through the cam, so let's see what's over on this side. Oh, there we have some more burnt and carbon-filled valves. The big one's the intake with a huge amount of carbon. The exhaust is a burned section in it. And we have another homemade sheet metal piece. This time not too bad, but nothing like the originals, of course. And we have what happens when the fan explodes. Even the fan can blow up, and of course when the fan blows up like this, it takes with it, 1, the fan shroud entirely, and 2, always the oil cooler, and sometimes 3, this flying fan blades that fly very close to tornado velocities can actually cut through the cylinder fins, and I've seen one Super 90 head ruined by flying fan blades like this. Even the fan doth fail. And of course we have our lovely head that sucked the valve guide boss and then broke the seat in half, and the resulting pieces going inside failing the piston, and then threw the rod through the case because of that. And speaking of more failures on pistons, we have many examples. But there's a regular super piston up above with the broken rings forming a ring-eating monster. And here's a big bore kit failing from its favorite way of failing, which is, of course, breakage of the ring lands, not the rings so much. And here we have the aluminum rocker stand, whereby if you use one head nut too many or one too few, you can get the effect of breaking a piece of wood over your knee syndrome, which is, of course, what broke this particular rocker stand. And then we have if we can zoom in all the way on this one, we have a spark plug that has been hit by the piston and the electrode dinged over. Here we have one that's an Autolite Ford plug stuck in a Porsche with way too much reach that the piston hit and dinged over the electrode. The next one in line up on top is part of the head around it, where it came out from the whole head coming out. And the final one is just another deformed spark plug. You see these occasionally too. If we zoom out again, we'll see here that even the movie stars sometimes have their own problems. Oops. This one is Jerry Seinfeld's problem. Even the movie stars are not immune to Porsche problems. He had this engine rebuilt in Los Angeles. It's for his 58 Speedster. Really kind of a mishmash of an engine. But anyhow, the fan, the inner pulley half of the generator fan combo broke, as you see. The fan belt came off, and of course with the fan belt goes all your cooling of the engine, as the cooling fan is on the other end. And when the fan belt breaks or falls off, then there's no cooling fan anymore. But Jerry kind of kept on driving it until not just the red light on the dash was illuminated, but the green light on the dash was also illuminated, meaning the oil pressure was way too low. When he brought this thing to me, the engine itself was in his 58 Speedster. The main case halves were a 59, and the third piece was a mid-57 that had the external oil booster line for the thermostat oil control valve. But the 59 set of main case halves didn't have anything like that. They had the later model separate removable pipe. So nothing was hooked up, which is probably the reason it had 15 psi under all conditions oil pressure, way too low. So anyhow, Jerry Seinfeld is now driving around with one of my 1973 souped-up industrial engines for the street and having a very happy time with it. Much better choice. But anyhow, what caused this problem here? And there's a shim from Jerry Seinfeld's engine also was failed along with the inner pulley half. I stacked the shim stack back together again. It was correct. You had at least 10 shims there. Usually 7 between the pulley halves and 3 between the nut and the outer pulley. And there were indeed about 10 shims here, so it wasn't the shim stack that was the problem. It wasn't until about it wasn't until about 3 or 4 months later, when I was using Jerry's generator on another engine, I happened to put on the nut to test the threads on the rebuilt Bosch generator. Nut went on about 3 or 4 turns and stopped, even though there are many more turns left unthreaded. I mean threaded, but not on it. The threads were all boogered up, so we ended up chasing out the threads. The nut would go on fine, but what had happened with Jerry's engine was they had put the fan belt back together again. They started to tighten the nut back up. The nut got tight. They figured they were done. It was nice and tight. But it wasn't. It was a bad set of threads on the generator shaft. And the pulley halves were not tight, so they flexed like crazy. And 47 miles later, it came apart, overheated, and died. So a 47-mile life, if you're a movie star sometimes in Hollywood. This is not an uncommon problem. Over here we have the remains of the hubs. The hubs are on the center part of the generator shaft, and they transmit the torque from the fan belt to the generator and to the fan, of course. In this case, these are both failed by an interesting little problem. You want to take the nut off of the fan on the other end. So people get the bright idea of putting this hub in a vise or putting vice grips on it and holding that while they put the 36-millimeter wrench on the fan nut and take it off or torque it down. Well, now, if that fan nut is rusted on, you'll find it takes a lot of torque to get it off. Enough torque so as it breaks the hub here, and or it decapitates the key in the keyway, and or it ruins the keyway in the generator shaft too, which means you just ruined your brand new rebuilt Bosch generator, and no warranty, no return on stuff like you ruined. And there you are, still stuck out in the boonies. You don't want to take the fan nut off with a wrench holding the hub on the other end. You want to take it off with an impact wrench, and ideally put it back on that way with one that can do torque, because it is really helpful. Otherwise, you'll end up with replacing your inner pulley hubs, your inner hubs, or your generators quite often. There's another failed one, and there you can see the beginnings of it, where the cord cutouts have started to eat through and form a circular hub there. And we even have a better example of that we can show later on, where the guy used the two outer pulley half hubs. Big mistake, and it wore a beautifully circular pattern in both of them. Looked like they were just perfect for Volkswagens, but don't work too well on Porsches. And then, oh, this is tremendous. We can get a good view of this. These are the Venturis from a Zenith carburetor. Actually, these are the Venturis from 5 Zenith carburetors. And my assistant go down, well, first let me explain this a little bit. Starting from the left, we have a fire started in the Zenith carburetor in all cases here. In the first situation, the first one on the left started just for a little bit of time and began to melt part of the Venturi. The second one from the left melted a little bit more of the Venturi. The third one from the left, if my assistant can grab that one and then tilt it upwards so we can see the wonderful area. Now I'll put it back on the, there, put that, that's right there. But tilt it out, that's beautiful right there, yes. You can see the actual Bernoulli equation represented in what part melted of the Venturi and what part didn't. And I'll bet that's a PhD thesis there in physics, fluid flow, heat transfer, all waiting to happen. And then the next one down, the Venturi has melted almost, pick it up, tilt it sideways, that's it. The Venturi has melted all the way down pretty much, and likewise the final one, again melted all the way down. But that middle Venturi, where it's only partially melted, we'd show that again, has a perfect description of the Bernoulli equation. Tip it vertical. All right, that's good. That'll be fine that way, just like that. And there's a PhD thesis for somebody right there. And we have the actual demonstration experimental object still on file. Okay, thank you, assistant. Here we have a rotor from an 050 that arced through to ground, so it's a great anti-theft device. A cap from an 050, the center terminal has died on. Other caps do the same thing, it's not unique to the 050. Another screw-on cap from a 912 C that belched its inner contents into the cam gear. And a nice original distributor, looks beautiful. But somebody, when they were taking off the pin that holds the drive mechanism in place there, they beat on the shaft too much, because it's a tricky pin to remove otherwise. And you ended up with the distributor shaft being bent, such that number 1 points for number 1 cylinder would actually open fully. Points for number 2, or the second one in the firing order, number 4, would open okay. The next one in the firing order would not open at all. And the final one in the firing order would barely open, making for a really strangely running engine. Meister changed it out and put an 050 in and found that solved the problem, even though he didn't know the guy had a problem until later when the guy told him. The drive gear on the left has razor-sharp teeth. You can see that on your big screen TV. Razor-sharp teeth. This is caused by a crankshaft that had worn about 20 thousandths of an inch on both the rods and mains from something getting inside the engine, like sand or beads or whatever. And it wore everything in the engine, including the drive gear, which never wears out. On the right, however, we have a drive gear that if you look at the drive section where the fuel pump drive is, above the geared section, you'll see the factory cutter, when he cut the teeth for the gear section, went a little bit too far and cut into the area for the fuel pump drive, which must have made a very exciting time for the fuel pump drive rod in this particular engine. It's a factory defect here that we have, another factory defect. Well, I hope you have enjoyed a close shot here of all these different parts. Let's zoom out. That make up a Porsche engine. We have almost every part of the Porsche engine failed, and there's a few more we're going to show you later on. Couldn't fit them in here. But you get the idea. I always leave a part out when I leave the shop here for fear this thing will come to life and attack my engines that I have at the shop. But as you see, in many cases, zoom in on it, sometimes the cause of the problem can be really, zoom in on it, that's it, Mickey Mouse. But a Mickey Mouse problem can affect you just as much as a real problem. There's a Mickey Mouse problem there. That one is certainly Mickey Mouse. And we'll end with our cam gear quiz. Remember that cam and camshaft we have here? Here are some of the boo-boos on that cam and camshaft. If you note, if you look at the bolt heads there, you'll see the retainers bend up around the bolt head entirely. But they're not supposed to do that. One ear is supposed to bend down inside in that hollow area where the slot is located to be actually a bolt retainer. As it is now, they're kind of bolt washers. They don't make it that way. Number two is you'll note that the dowel pins look a little funny because they're really not the right dowel pins. They're actually crankshaft dowel pins, not camshaft dowel pins. Number three, you note the dowel pins have a groove there right by them. All three of them have this funny groove. Why did that happen? And finally, number four, we'd have my assistant trace the center slot where it goes out to that bolt hole in line and keep going to the edge of the cam gear. It's supposed to be the timing mark, which isn't there. Where is the timing mark? Where's that little zero? The assistant find it? There it is. It's over there. So the extension of the slot does not point to the timing mark. The cam gear is on wrong, and lo and behold, that's exactly what happened. The first time this guy, well, let's go down to the Rosetta Stone of cam gear defects. There's a Rosetta Stone of cam gear defects I found this problem from. If you note, when the thing first came in, the cam gear had been bead blasted, so it was nice and clean. That was very important, because the gouges you see there on the dowel pin holes were the same as the gouges on the other camshaft, and the guy asked me how come this happened. I looked at that, and I could tell from the bead blasted cam gear that no bolt had ever been in the holes. And because of that, they put the cam gear on the camshaft with just the dowel pins, not put the bolts. And the cam gear came off the dowel pins. I said, who was the idiot that put the cam gear on the camshaft without putting the bolts in place? And the customer said, he was. Well, he admitted it, so I gave another cam gear in exchange for this one just to have this for show. It taught me what happened in the first case. First case, they put the cam gear on with only the dowel pins without the bolts. It came off in 47 miles. So they put it back on again, using the bolts this time and the retainers, but the wrong way, and they couldn't use the dowel pins anymore. They had to use the crankshaft dowel pins. The ones have been smashed coming out. And when they put the cam gear on in their haste, they put the cam gear on wrong. So the engine never started. So they sold the engine to the next guy down the line. He brought it into me. I could tell the cam gear was on wrong, but I didn't know why these little gouges were until 2 weeks later, because things come in pairs. I saw this one. That's right, and there it was. It taught me that keep your eyes open. You think you know everything? Something will come down the pike you've never seen before. Because fools are so ingenious, they can make things up that you can't possibly conceive of in a million years. And they'll do it consistently. So every time you think you've seen it all, no way, there's something else to see. Makes life great, doesn't it? Thank you for watching this videotape. We'll zoom on out and show you once again the total disaster that turkeys can do, or fatigue in some cases, can do to your particular engine. Broken cranks, thrash cases, thrown rods, broken cams, broken push rods, badly repaired push rod tubes, broken heads even. One disaster after another, and even movie stars are not exempt from this, as Jerry Seinfeld knows. Actually, a few others too. If you have any questions about this videotape, it's done by HCP Research, 320 Martin Avenue, Santa Clara, California, 95050. Our phone number is area code 408-727-1864. You reach us by email, maestro@well.com. Consequently, we wish you all a good one. If you don't want to have these kind of problems inside your engine, we're happy to do it for you. Or if you want to do it yourself, we're happy to do the parts, machine work, or whatever. Even offer free advice You pay for the phone call, please. That's 408-727-1864 or maestro@well.com. All small letters, MAESTRO, the @ WELL.com. For our email address, our fax number, area code 408-727-0951. Thank you for watching, and keep the 356 faith. Okay, well, here we have the 356 Porsche engine exploded view, using an engine that's made up of parts basically from every disaster that I've seen in the past 20 years, including a few new things thrown in since last time. You know, this is a interesting operation when you see that Mickey plays a role here. M-I-C-K-E-Y, M-O-U-S-E. Right there. Sliding to the left of Mickey is a very interesting problem. Yeah. But we'll get to him in a second. How about to the right of Mickey? Let's go over and see. Oh, we see a sculpture here. Oh, yes, a sculpture. The Seinfeld sculpture. The pulley in the center with a big hole out of it, and the two mustache-like pieces on opposite sides of that pulley happens to be Jerry Seinfeld's own pulley half, inner pulley half, from his 1958 Speedster engine. The engine was actually an average 58 Speedster. It had a 59 set of main case halves and a 57 third piece, so it averaged out to a 58. But of course you can't do it that way. Yeah, it took a while for me to figure this out, but it turned out that what happened was the generator shaft on the Bosch rebuilt generator, the threads have been screwed up somewhat, and the pulley nut would go on little ways and not fully, but it would feel like it was tight. So the people who rebuilt his engine left it that way, and of course the inner pulley half fails and takes with it the fan belt, so he lost his cooling. And at 47 miles, his engine basically fried itself. It was a real mishmash of parts anyhow. He's running around now in a 1973 356 industrial engine, souped up and converted for street use. And he's very happy with it. In fact, I just talked with him today. And over here we have the smile. Actually, it should be an unhappy face, because this shows the progression of standing wave fires inside the Zenith carburetor venturi. The progression goes from a little bit of melting on the left to a little more melting on the right, to a really beautiful trace of the Bernoulli equation in the middle, to it melted fully on half the venturi until it melted like 3/4 of that particular venturi. These are Zenith carburetor venturis. For some reason, they have this steady state capacity of forming a standing wave fire right in that venturi. Of course, I have a few melted Solexes and Webers too, but that's another story. We also here have something you won't see very often. An SPG roller bearing crank. Somewhat rusty, original rust too. It serves as a perfect doorstop. In the summertime, it's really nice to have that for a doorstop. The rod's a wedge into the ground, and the door will not be able to be blown shut by the wind. Other than that, or a boat anchor, I don't think it should be used in a 356 or 912 Porsche engine. Going along with that, of course, we have the flywheel with the dowel pins that have been decapitated, all 8 of them sheared off when the flywheel nut broke or otherwise came loose. The guy was actually lucky, just threw in the flywheel. The dowel pins were sheared off in the crank, but the holes are not elongated, so actually his crankshaft was fixable. Now let us zoom in on some very interesting bearing problems here. The one on the bottom of the screen, the bearing with a shims next to it, is a rather interesting case. It was a 912 installed in one of these kit car Speedsters. Actually, the Speedster kit car was actually quite nice. But people in L.A. had rebuilt the engine, and they obviously used the Volkswagen shop to do it. And what these are, the shims on the right, the three thin shims, are actually not VW 36 horsepower shims. It actually would have functioned in a Porsche, sort of, but you really want to use one Porsche shim rather than three 36 horsepower VW shims. But those shims shown here were 1500, 1600 VW shims. They're way too big. They're obviously the wrong size. And you see from the marks on the flywheel main bearing, a number one main bearing, that it barely touched the outside circumference of the main bearing, and it barely touched the flywheel, too, on the other side, and it would have failed miserably very quickly. Fortunately, the owner of the Speedster had me overhaul it before that happened, and we were able to save the case and all kinds of disasters. But that's the kind of work you sometimes get in the LA VW shops. Right above it is my favorite boo-boo. That's a number 3 main bearing from a 50-millimeter crank used in the AB normal Supers from like 1950 to 1963 normal and Super. You note on the left-hand side there's something sticking out of what appears to be the bearing, and that's correct. What's sticking out is a dowel pin. You note on the inside of the bearing you'll see an oil hole, and opposite another oil hole with a dowel pin is stuck in, and to the right on that bearing you'll see the dowel pin hole, which is a blind hole. It does not go all the way through. Well, what happened was when the guys were putting the crank into the case, they weren't paying attention to what they were doing. Instead of putting a dowel pin hole on the dowel pin, they put an oil hole on the dowel pin. This may not seem like much to you, but we have other examples, too, of bearings that, yes, we should show them, too, shouldn't we? To have the progression of the problem where the dowel pin actually gets forced into the crankshaft by the oil pressure behind it. And this can only happen. You run through the math on this from F equals MA in physics, and the size of the dowel pin is mass, it's oil pressure, the cross-sectional area, blah, 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 how long it has before it can go into the hole. And the hole in the crank is only a little bit bigger than the hole in the dowel pin, or the dowel pin size, so it's not obvious it's going to go in immediately. It turns out that you cannot get that dowel pin in that crankshaft when that crankshaft is spinning more than about 290 revolutions per minute, which means when it's running at 1,000 RPM or idling at a minimum of 500, it's well beyond the range of where that dowel pin can go into the crankshaft. But it can go into the crankshaft, and I have examples or pictures in Murphy of that very thing, of the dowel pin, this dowel pin here, one like it, inside the crank. And when it goes inside the crank, it'll actually come back out from centrifugal force when it's running and machine the inside of the bearing, this number 3 main bearing. And all the pieces will go throughout your engine, and they're, of course, once again, they're aluminum. They go right through the magnet, right through the bypass oil filter, because it doesn't go to the bypass oil filter, it goes right to the bearings. And you have a mess on your hands. This particular problem can be avoided by paying attention to detail, like this one over here. Now, these are the 2 small main bearings of the number 4 main, and you see that the dowel pin bolt has been missed, and a new hole has been reamed into the number 4 main bearing. Note that when this happens, that you deform the bearing quite substantially, especially the other side of the bearing, too. You make it oval shaped, all kinds of bad things happen. The crankshaft rubs against the bearing, it grabs bearing material and forces it back into the bearing. It makes a real mess. You can see from the inside of both bearings are really badly scored up. And they're scored up because the dowel pin bolt did not go into the hole right. I bet the women are very happy to date these guys that do these sort of things. It must be very gentle. If it doesn't go in, force it. And here we have our expanded oil cooler, where the oil cooler was pressurized to some unknown pressure, but somewhere probably around 1,000 pounds per square inch, and bulged at the top quite significantly. Let's go over to the other row of bearings here that I think you'll find the evolution of failure is rather interesting. All right, now on the left hand, we'll start from the left and go to the right here. The left-hand guy, this is the evolution of the failure of the thrust surface of the flywheel main. There's a dowel pin hole up on top, on the left one, and there's some wear of the thrust. The next one in has more wear of the thrust and has more wear of the dowel pin hole. This guy here, number 3, has even more wear of the dowel pin hole, and then finally has really significant wear of the dowel pin hole, and then tremendous wear of the dowel pin hole, followed by tremendous wear all the way around, destruction of the thrust surface itself here, and just real disaster. And finally we have the evolution of the ultimate product of Murphy's machine shop. That, of course, is the number 1 flywheel main where the crank broke in half, and this whole circular section was extruded out to about 10 times its original length, and about 1/10 its original thickness, of course. Also the dowel pin, you can see the remains of the dowel pin there. The dowel pin burrowed a furrow all the way around that number 1 flywheel main bearing. until finally it was closing the passageway behind it as it went, and just a little bits left on the left-hand side of open oil passageway to oil the rod that was off of the #1 rod here, and he ended up just making it back to his driveway before the engine was completely fried. And once again, you can see on the left, razor-sharp teeth. That is to say, this engine had a lot of wear particles in it from a crank, worn about 20,000th of an inch. Cam gears all worn, all kinds of stuff inside. And it just ate even things like distributor drive gear down to razor sharpness of the gear teeth. Compared with the other one, which has an interesting defect, where in the factory when cutting the gear teeth, went a little bit too far, had to miss a line, and the gear teeth were actually cut into the drive part of the fuel pump above those gear teeth. And that shouldn't be there. Note the other one on the left doesn't have that. Well, there are two rather interesting defects here. And then we'll have to take a break, because here comes the 633. Once again, here we have the 356 Porsche engine, exploded view, made up of parts that are quite badly broken. We're continuing this tour here with a look at an interesting man-caused, human-caused problem with certain main bearings, in particular #3 main of the 356 AB normal super from 1950 to 1963 in normal super vintage. This is the bearing that goes on in front of the gears on the crankshaft. And you look very carefully at that one on the top, completely circular bearing. The one on the top has what appears to be a dowel pin sticking out of it. And yes, indeed, that's exactly what it is a dowel pin. If you look over at the hole on the right, you'll see that hole on the right is a blind hole. That's the true dowel pin hole where the main bearing is supposed to go on. But the guy wasn't paying attention, so he proceeded to put the #3 main bearing of the AB normal super crank, 50 millimeter main crankshaft, onto the oil hole of the bearing. So the dowel pin is kind of sometimes loose in the case on these particular engines. And sure enough, it wiggled free and ended up being stuck in the bearing like that. And the second one from the top, you'll see the dowel pin being stuck in the bearing. And you'll see how it's actually chewed some of the inside the bearing up. In the third one, you can see more evidence. In fact, down there inside the bearing is, in fact, the half of the dowel pin. The other half having been worn off or otherwise decapitated by the action of the crankshaft. And then here up on top, here we have yet another one where you can see the dimple in the bearing, in the oil groove of the bearing area, or the oil groove area of the bearing. The dowel pin has actually been forced through it practically, breaching it. Even more amazing than this is the dowel pin itself can go inside the crankshaft. If you run through the numbers and the physics of it from F equals ma and the mass of the dowel pin and the oil pressure behind it, and how long that window of a turning crankshaft will allow the dowel pin to be spit through into the hole its own length, you end up with the fact that that dowel pin cannot go in that crankshaft when the crankshaft is operating at RPMs above 290 RPM. Well, the lowest possible idle you have here on a Porsche engine is about 500 RPM. It doesn't get down to 290 normally, so how does that dowel pin get inside the crankshaft? Then continue with this bearing here, and from once the dowel pin's in the crankshaft, comes back out again, acts like a machining tool on the inside of the bearing when the engine's fired up again. Ends up machining the inside of this bearing like you see here. In fact, in one case, a dowel pin on an early B crank, where the oil holes are drilled from the rod direct to the main without the cross-drilled pattern they use later, the dowel pin actually can be forced into the rod bearing area, and I have a rod bearing that has a beautifully machined center section caused by the dowel pin acting like a machining tool on the rod bearing all the way through the crankshaft. Anyway, this one here stopped at the main. But getting back to how the bearing, dowel pin gets inside the oil hole of the crankshaft, it turns out that yes, the engine does come down through 290 RPM when you're cranking it, and on the way up when you're starting it, but oil pressure is not established when you're firing it up first, so that doesn't really apply. So what happens really is that dowel pin goes into the crankshaft oil hole when you turn the engine off. One of the few times when turning your engine off can hurt it, but it's one of them. As the engine coasts down below 300 RPM, there's now time, oil pressure is still established, to fire that dowel pin into the crank. And that's exactly what happens. End up with the dowel pin inside the crankshaft, machining the inside of your bearing, All the chips in that operation go right through your engine. Remember that bypass oil filter? Now the full flow goes right to main bearings. Do not pass filter. Do not be removed. And you end up with something like this. Now you note what we have here are 5 bearings, and I think I have another 1 or 2 floating around, that have had the same problem whereby the idiot that was rebuilding the engine wasn't thinking about what he was doing. He was talking about his hot date that he had night before at the VW shop or whatever. And when he puts the bearing into the case, the bearing's on the crank, so he's laying the crank into the case. He's rotating the bearing, number 3 main bearing, you get on his dowel pin. Thing goes clunk. Does he pay attention to make sure that he rotated the dowel pin hole of the bearing, the blind hole, on the dowel pin, or does he just kind of do it randomly with his eyes closed or not even looking at it? Probably the latter. There's 1 of these bearings per engine, so this is 5 engines had this happen with. Not the same engine, 5 different independent engines. Probably the only common mode of this it was done by perhaps a VW mechanic. Also, we will stop for now. Well, there's something else interesting about this number 3 main bearing that goes on in front of the gears of the crankshaft before the gears go on. On the 50 millimeter crank using the AB normal super from 1950 to 1963, the dowel pin is now correctly arranged. The dowel pin hole is on the left-hand side there, at the hole in the middle of the bearing there. The one at the top contains a dowel pin that was put in the oil hole improperly, and the one at the bottom contains a second oil hole. Now, if you were to put your finger in that dowel pin hole on the left, the blind one with the dowel pin should normally go, and rotate the bearing around that axis, like with a pencil in it, in the blind hole where the dowel pin would normally go, you would find that those oil holes, top and bottom, are not symmetrically arranged. And there's a reason for that. The reason is, in an operating engine, the crankshaft is rotating clockwise in the Porsche engine. It's trying to climb up the right-hand side of that bearing. Bearing is fixed in the case, remember. So it gets a little ways up and it slips. But the equilibrium position is a little bit to the right of bottom dead center of that bearing. Well, isn't that interesting? It's right where the oil hole is located there. If you put that bearing on that way, then lo and behold, the oil hole is lined up the way it should be. And if you put it on the other way around, you'll find out the oil hole on top will be in the left-hand case F. And the oil always has to go all the way around the case there to get to where the crankshaft is on the right-hand side. So this is mentioned in the factory manual. There's a 50-50 chance of putting this bearing in wrong, assuming, of course, you put the blind dowel pin hole on the dowel pin. And, of course, when Murphy says it's a 50-50 chance, 90% of the time it's wrong. So you're putting on a number 3 main bearing onto a 356 AB normal super crankshaft. Please remember the oil holes are asymmetrical for a reason. And arrange it such that the oil hole, look at the case with the bearing in front of you, and see where the crank's going to rotate clockwise. See it climbs up the right-hand side, and put that oil hole there in the right-hand case F. Then once you realize that, stick that bearing right over your crankshaft, and there you are. And then put the gears back on it. But these are 5 different bearings, 5 different engines. It's not 1 in a million. It's 5 out of 100 of 1,000 here, and probably more like 10% of all engines have this problem. Okay. Next on the list, we have a couple of new additions here we would like to show you. Let's zoom out so it's possible to see what we try to show you. All right, now this interesting little mouse-like structure is made up at the top of a guy who used 2 of the same pulleys, either both outside pulley halves or outer pulley halves rather than inner pulley halves. And note how the engine didn't like that very much and machined out a perfectly circular opening. These form the eyes, by the way, of this sculpture, in case you couldn't figure that out. This is why you don't want to use 2 outer pulley halves instead of 1 inner and 1 outer, because the inner and outer are designed to go together, but the 2 outers and 2 inners are not designed to mate with the same guys, you know, the same people, sort of. This may be a lesson in life, too, for you. And there's, of course, the phone, which has been a random problem throughout the afternoon. This smiling structure is made up of rather defunct Porsche parts. The top 2 eyes are, in fact, the both outer pulley halves of a 912 engine that the guy didn't know the difference between inner and outer pulley half, ended up using both the same pulley half. Well, this same-sex pulley half combination, of course, does not mate right. You end up with the fan belt reaming out, or actually the center hub of the generator reaming out the center section of both outer pulley halves and forming these little eyes. They should have the 2 cord cutouts. We don't want to mix up the pulley halves. You want to use an inner and an outer, not two outers or two inners. It doesn't work that way. Now, of course, the center pulley half in this picture is the inner pulley half from Jerry Seinfeld's engine, along with the two victims of the shim that had broken in half, too, as the fan belt was leaving. This is caused, of course, by the shaft of the generator, the threads of the shaft of the generator, not being dressed properly on the Bosch rebuilt generator, and ended up with the nut going on what they thought was tight after a few turns, when in fact it wasn't. Then the pulley halves were not tight enough together, and the inner pulley half did this, and the fan belt went bye-bye, and the red light comes on the dash. But unfortunately, the driver did not stop, so he kept going, and the green light came on the dash, and that's when the engine and car were shipped up to me. Jerry Seinfeld is now running around with a 1973 industrial engine, rebuilt, so it looks like a 58A Speedster engine pretty effectively, and he's happy as a clam. Moving along here, the other direction, the teeth there are actually the Venturis from Zenith carburetors. And here are at least 2 or 3 PhD theses just waiting to be written on fluid flow, thermodynamics, heat transfer, etc., standing wave fires, flame propagation, all kinds of stuff. But if you look from these are all the Venturis from 5 different Zenith carbs. On the left, you see the standing wave fire had started at the Venturi from probably a bad intake valve or a backfire, and it melted, just begun to melt part of the Venturi. On the second one, you see the Venturi has been melted further. On the middle one, you see not only has the Venturi been melted, but formed basically the equation, the Bernoulli equation, in a sculpture. And that particular third Venturi there, I think you can write many a PhD theses about. Number 4 is where the fire continues a little further and melts the remaining structure. And number 5, likewise, a little bit further and melts even more of it. But as you see, you can get a standing wave fire inside a Zenith carburetor where it's burning continuously while the engine is running, even a high velocity air fuel mixture going through there. And that can cause enough heat transfer to the Venturi, despite all the cooling effect of evaporating gasoline, to actually melt the Venturi and describe the Bernoulli equation while so doing it. So describing that wear pattern, that burn pattern there, certainly is worth at least three PhDs at prestigious universities. Remember where you got the idea from. Okay, here we have a cap from an 050, but it'll serve as a cap from a 009 or an 022 or whatever kind of distributor you might have. They do suffer eventually after a long enough time. The more modern caps seem to suffer more. If you look at the center electrode of that cap, you'll see it's all eroded from the spark activity there. And it was not arcing, is not providing enough decent pathway for the current to go to the right contact, so you had misfires. The rotor is a great anti-theft device because it looks not too bad, but actually was arcing all the way through the center section to the center shaft of the distributor and thence to ground. So that being the center spark plug wire, no spark ever got to the spark plug, even though it appeared like it had spark when you did all the standard tests. So it took a little while to find that, but not overly long. But if you park someplace, you can pop your good rotor, put it in your pocket, and put the old rotor in there, and then nobody can start it. If they're smart enough to even figure out it's a problem, how would they ever guess where the rotor is? And if that's it, and if it is it, how do they replace it? I guess the same thing can be had by taking the rotor out, but then immediately you took the rotor out. This way the rotor's still there. You can fake them out even more. Great anti-theft device, though, some of these 050 parts. Don't get me wrong, the 050 is a very nice distributor. I like it very much, but sometimes it pays to get a spare cap and rotor with you, like on a long cross-country trip. Here we have, of course, the aluminum rocker stand. The magnesium one we showed before breaks and pulls the stud out of it because their magnesium is not strong enough to be used in this particular application, so they changed to aluminum. But you know, this one's broken. This, of course, occurs when you leave out or put in one too many head nut washers when you're putting the head nuts on, the lower row. And then it's like breaking a piece of wood over your knee when you try and torque down the rocker stand and one end is sticking up way high and you got something way down below or way up above. Isn't that right, Mr. Troy? You had an experience with this, didn't you?
Firsthand.
You actually made that particular sculpture yourself?
I had used a one head nut to retain the head while I got all the rest of the hardware on, and I forgot to remove the head nut to put the washer under.
And there you have a mea culpa from Mr. Richard Troy himself there. Frankly, I've done one of these too. I didn't notice that the head nut had been ground down before. That's why it helps to look at all your head nuts, because even they crack too. In fact, I can show you some cracked head nuts also. And when they crack, they leak oil usually through capillary action down past the seal and on your engine and push rod tube. You think it's a push rod tube leak. It's very subtle. But you got to check out everything when you put it together and make sure somebody hasn't been there before you messing it up. especially Super Turkey. You see him, after all, he's responsible here for most all of these parts going bad. And he's around, he's all over, he's like Murphy. He's Murphy's constant animal companion, Super Turkey. Yes.
You should also be aware of very early engine cases have a different length head nut. So you should, when working on a two-piece engine case, always beware to measure them very carefully.
Well, not just a two-piece engine case either, because all the A's didn't use any head nut washers. So all their head nuts are one silly head nut washer's thickness longer. And the infinite number of possible screw-ups you can get with that, and interchange them with the later head nuts that are shorter, with or without the washers on the heads that take them or don't, you have an interesting combination that PhD philosophers will philosophize over for years. You do it right according to videotapes. I like to use the washers with the later head nuts. The later head nuts tell you they're later head nuts because they have a machine ring around their shank, and we can show that too. While the A head nuts do have no machine ring anywhere on its shank, and are about 2 millimeters longer. One head nut thickness is 2 millimeters on a head nut. And incidentally, head nuts I have, quote, head nuts, I have them varying in thickness from between about, a little over 40 thousandths of an inch, 1 millimeter, to beyond 3 millimeters, or about 1/8 of an inch. Some of these obviously are homemade. The standard head nut is 2 millimeters thick. It varies from 79 thousandths of an inch to 81, depending on where you buy them, what style they are, if they're chrome plated or not, blah, blah, blah. I like to mic the head nuts before I put the engine together and arrange them so that the good ones are right around 80 thousandths of an inch, 2 millimeters, get underneath the important head nut, the lower row of head nuts. And that the other ones that aren't so good can be used on the top row. Now they're critical there, but it is nice to put them all together with 79 to 81 thousandths head nuts. That way everything works pretty well. Do you mic your head nuts, washers, before you put your engine together? Maybe you ought to, and you get a real surprise sometimes. Okay, now those little pieces of bronze jewelry you see right in the middle of your picture there are rather interesting. Above it you see a full valve guide that's starting to banana peel. That is, the end of the guide is starting to peel off like the skin of a banana. And what happens when it fully does peel off, you end up with pieces of that guide coming out and going inside your intake valve area. Well, if they're too big, they won't go through the intake valve. They'll bounce back and forth in the intake valve. And they get highly polished and smoothed out, like you see these 3 pieces here. Well, you can almost make earrings out of them. All caused by Murphy's machine shop, where the intake valve kind of bounces the piece of the guide around and polishes it. Now, eventually, the guide gets small enough so it goes through the intake valve, gets beat by the piston, decarburizes the head and the piston, it goes out the exhaust valve. And if you don't notice it, you think, oh, well, that was lucky that we had rod knocked and it went away. What will happen is the whole guide will eventually come out, and you have a hole in the head about 1/2 inch diameter. And you get the piston sucking on the hole in the head when the intake valve is open, and you suck in all kinds of oil droplets, which then piston compresses them, and the spark plug ignites the fuel and the oil mixture, and you become a smudge pot. You're able to blast out behind you enough smoke to cover any of the Enterprises, the aircraft carrier, the space shuttle, or Star Trek. All from a valve guide that gets sucked through the head, and the pieces bounce through the chamber. Okay, now this one here is a Hauserman pressure plate. These are available in the A series and some early Bs, 1960 or so. They're a diaphragm pressure plate, one of the first diaphragm pressure plates Porsche used. They're used on the A Supers and, like I say, sometimes the B Supers. The A's had a collar that went in the middle of these fingers here in the center. Their failure mode is a crack outside by the outside surface. The circular holes you see drilled in there at the end of the fingers sometimes crack there and go all the way on the outside. The diaphragm dies, and you lose your clutch. Very common problem on Hausermans, but you hardly ever see these Hausermans pressure plates anymore. They're very, very hard to find. They do work nicely, though, with the collar on the A's for a 180 millimeter clutch. It actually works, as opposed to the spring-type BW with the 6 or 9 coil springs. This is a much better unit than that, but they're, like I say, they're extremely rare. There's also a 200 millimeter Hauserman diaphragm pressure plate used on the Carreras. And they would actually fit 356Cs, but they're hen's teeth also. But this is a common failure mode of the Hauserman pressure plate. All right, this one here is a Weber 40 IDF carburetor. It's one of the ones I like quite a bit, but they do have their own problems. Though they have the throttle shafts have ball bearings at either end, and the throttle shaft wear is a thing of the past with Webers, and the jets are really easy to change and all that sort of thing compared to Solex's or Zeniths. They have one inherent problem you should know about. If you look down by the bottom where the base of the carburetor is, you'll see that there are these two plugs. Actually, there's one plug. There's a lead plug in the left-hand hole there, but there's an open one in the right-hand hole right in the middle, just below that plate, rectangular plate there. Now, what happened was a soft plug came out. And these soft plugs are used to plug passageways that the factories drilled to make some of the various holes. And when this plug comes out, the float contents of the float bowl come out all over your spark plug wires. And the contents of the float bowl, of course, is gasoline. So you end up having gasoline all over your spark plug wires. And it really suffers badly because of that. So if you have Webers, it's nice to, brand new ones even, it's nice to put some epoxy over these plugs so they cannot come loose. You may save yourself a car or an engine or some combination by plugging those, not plugging, but putting a prophylactic covering of epoxy over those plugs so they cannot come out easily. Now here we have a Solex 40 PII carb. You guys with Solexes don't get feeling superior over Webers because you don't have that problem. You have an equally bad problem. You see on the right-hand side, in almost the same place as the Weber was, a little bit further to the right, you'll see a brass plug in that Solex. On the left-hand side, you'll see there's no plug there. That's because it fell out. When it falls out, even more insidious problem results. It doesn't leak gas, but it sucks air. And a part throttle application that runs too lean can very possibly affect your engine and fry your pistons when the Solex soft plug comes out. Here's another area where you have to put a prophylactic epoxy on or some type of sealer to keep those stupid plugs from coming out. And you Zenith guys don't think you're immune too, because Zenith has soft plugs that also leak and drool and cause gasoline to evaporate before it drips so you can't ever find it. So when you see the soft plug, it's very good on the carburetor overhaul time to go through and put clear epoxy or something over those soft plugs and make them stay in. Now we go a little further down here. You see a fairly common problem with an intake manifold gasket. I see this all the time. I don't know how in the world they're crazy like this, these guys that build some of these stupid engines, but they are. You have a CSC 912 or Super 90 head with the big intake ports. So what do you use for a gasket between the head and the intake manifold? That's right. You use a B-type gasket, which has smaller intake ports, so it acts like a restrictor orifice on the cylinder head, and you lose quite a bit of power because of that. Also, the droplets from the accelerator pump get stopped by this dam that's sticking out there, and don't go into the head right, so you get hesitations off idle and all kinds of crazy things. So overall, you got to use the right gasket. It's really not hard to find the right gasket. You put the thing on the head and see if it covers up any of the ports, or you put it on the manifold and see if it does. It just takes a few seconds to see if it does or not, but you'd be surprised how many of these I have. Almost every other engine has this problem. If it's a CSC 912 Super 90, they use the wrong gasket. In fact, there used to be 3 gaskets in the top-end gasket set. There's one with the circular hole for the early normals. There was one for the oval-shaped hole for the Super. There's a big hole, of course, for the SC 912 Super 90. And I saw one engine where the guy used all 3 gaskets, one on top of each other. And, of course, like a chain having the weakest link that causes failure, the smallest gasket hole predominated. That was the early A normal with the round intake ports, and he made his CSC 912 Super 90 into an A normal because of that. So please use the right gasket. It's not that difficult to do. And we have books like Secrets to the Inner Circle or the Engine Assembly Videotape to show you how to do this right. All it takes is a little bit of common sense. You'll avoid most of these stupid problems. Oh, yes, and before I told you about how the gasoline hammer effect, like the water hammer effect, can produce pressures on the order of 20, 30, 40,000 psi and bend those connecting rods we saw before. But also, besides bending connecting rods, I mentioned it can split cylinders or it can crack pistons. And as you see here we have a piston cracked, also from the gasoline hammer effect, and a cylinder, actually an SC912, very expensive nowadays, cylinder split down the middle because of the gasoline hammer effect. You don't want to mess with that. If you ever get that problem, and you end up with a gasoline in your cylinder, parked on the hill, facing uphill, resist the temptation to try and coast it down the hill and pop the clutch. What you want to do is, number one, disconnect the coil so no spark could ever be formed. Find the cylinder, let the top dead center or near it, and pull the plug out of it. And with no juice to the coil, crank the thing over to force the gasoline out. Replace the plug, let the gasoline evaporate, put the plug wire back on, hook everything up, and fire it up then. That saves your engine, and saves your engine from having things like cracked cylinders, failed pistons, like the bent connecting rods that we have here, right below here. Both of those connecting rods were bent by the gasoline hammer effect. It's nothing to sneeze at. The Alaskan pipeline once, when they were testing it with water before they used oil, they sent water from the Perdo Bay down to Valdez, but one swing check valve had been installed incorrectly. So when this wall of water hit the swing check valve that's installed backwards, it swings shut when it shouldn't have, but it did. And that swinging shut of the check valve caused, in fact, water hammer, real water hammer, to make the Alaskan pipeline, about 16 miles of it, jump about 15 feet out of its ditch. And that's a lot. The ditch was pretty deep, too, because of the gasoline hammer effect. You didn't hear about that in the news media, perhaps, but the boys who work on 356 work all over the world on various projects, and one of them told me that story. You want to check the details? I'm sure you'll find that'll be correct. You end up, if you're not careful, with either bent connecting rods and the gasoline hammer effect, or cracked cylinders or cracked pistons, among other problems. One last thing before we run out of time here on the camera, battery. We have a picture here of two studs in the Porsche case. And one has been necked down, very interestingly, by touching the cylinder wall and getting too hot and actually pulling apart. The other one is necking down. You can barely see there maybe at the end where it got suddenly smaller, where it was touching the cylinder fin, got really hot, and was starting to stretch and pull apart. When this happens, it loses its tension, and you end up with the head nuts not sealing anymore, and a head leak, and maybe exhaust gas in the heater system, and death for the driver in case he has the windows rolled up and doesn't smell the exhaust fumes. But little things like this, when you put the engine cylinders on, you're not supposed to let the cylinders touch the cylinder studs. The hole is there for a reason. The stud should be centered in the hole and not touching the fins of the cylinder or any part of the cylinder, because the cylinder gets hot and will transfer the heat. Okay. Now, I know you guys are probably depressed by now, seeing all these broken parts here and broken in horrible ways. Maybe even scared to drive your 356 or 912 Porsche home. But as I said in the past, we got to the moon on a rocket made of 1 million parts, each one made by the lowest bidder. So certainly a Porsche engine can be made to go a reasonable distance, like say maybe equal to the moon and back or so. Anyhow, when you get one done, after doing it properly, you will find that it may look like this. This one is destined for Canada. It's pretty much a run-of-the-mill hot rod Maestro massaged engine. Kind of like that plane taking off there. This has, in fact, one of the few rare original distributors that are still good. It does not have too much timing advance or sticky downwards or whatever. It actually does function. It's, of course, 6-volt system still. This one has the 44 IDF Webers and, of course, a big bore kit. We're trying out the forged big bore kits now. 86 millimeter, about 9.3 to 1, 9.4 to 1 compression. That vicinity. It sounds pretty healthy. It's going to Canada, where those winds sure do blow cold way up there. I talked to the man yesterday, and he is witnessing a big snow blizzard up there in Canada, the 4th in the last month. So wherever you are, it's probably worse where he is. Anyhow, let's take a few close-ups of this guy. That way, that's it. Note there's always a fuel filter on a Maestro massaged engine. And so these are the 44 IDF Weber carburetors. We use the Weber manifolds. The Weber manifold is really designed for the 44s. They're 44 millimeter bore on the manifold, really. You shouldn't use the 40 IDF Webers with the Weber manifold. You should use the 40 IDF Webers with the Adapto plate and the Solex manifolds. But this is a hot rod engine. We went with the 44s. They require use of the Weber manifolds, and there they are. Note the inlet fuel line is new. The fuel filter added. The decals. Over on this side, this is the tricky side on a Weber 40 or 44 IDF, especially one using the manifolds. You can zoom in there as far as we can go. Barely see the outline of a couple of bolt heads on that spring plate. Note how close the bolt heads come to that cover on the inside of the Weber, the left-hand side there, right about where that linkage arm is located. Naturally, it's right in the way. But anyhow, the bolts come very close, but if you trim the heads of the bolts and use thinner washers there, you can actually get it to not touch and make the Weber 40 or 44 IDF carburetor work on the manifold. But like I said, it's better to use for the 44s, which these are, the Weber manifolds. And for the 40s, which these aren't, these are 44s, then you want to use a Solex manifold. So let us zoom out of here a little bit. It has a carburetor heater system. The rear plate's not hooked up so you can see it. Note the arrangement of the dipstick shroud. That was the correct way of putting it on. Zoom in on that. Maybe. Dipstick shroud goes on top of the other piece of sheet metal, the cylinder shroud. So first you put the cylinder shroud down, then you put the dipstick shroud down. Likewise, on the fuel pump side of the engine, the same thing applies. This is, of course, a new fuel pump. That way there's not a problem for 100,000 miles. You can forget about fuel pump problems with new fuel pump. Penny wise and pound foolish to do it otherwise. That's the original distributor for it. New fan belt, powder painted sheet metal. And let's see, who did this guy? Oh yeah, HCP Research did this one. Under decals. Yeah, it's not too bad a runner. It really sounds healthy. 6-volt coil. Original plug wires with the bona fide Porsche ends. Those Porsche ends over there you can no longer get. They're unavailable and Burrow won't make them up anymore, so it's catch as catch can on the ends there, boys. You've been fair warned. Another Porsche part not being made again. Note the way the plug wires are tied down to the sheet metal. And there's a O-ring on that end and an O-ring on that end. Likewise on this side. Likewise on this side, there they are. You can see both at the same time. The little rubber tunnel with a tit on the sheet metal piece and the two tie downs on either end and the original spark plug wires. And there's a rod coming through from the heater system for the carburetor air heater system. It goes to the rear plate and controls the flapper valve. Now if you note, that little rod actually has a little hump in it right near the fan shroud. You look at the shadow. And that little hump is there for a reason. It doesn't look like it has a reason here on this engine, which it really doesn't, but why do they put that little hump in that piece of that connecting rod that connects the thermostat to the flapper valve on the rear plate? Question for this week. All right, we want to show you that at least it's possible to make something that works. And it's still possible to do that pretty well, as you can perhaps see here. I'm not in love with that exhaust system, but that's what the guy specified. So if he specified that, that's what we put on, as long as it doesn't affect the engine. The 2-into-2, I like to see the 2-into-1, or I'm sorry, the 4-into-1. This is a 2-into-2-into-1 system. But it's supposed to be fairly quiet. He wants to drive it in the street, too, so it's a compromise, and I hope he likes it. Anyhow, we'll get back to some broken parts after this, but at least here is at least a halfway reasonable engine, leaving for Canada on a 727, I guess, coming up here in about tomorrow or the next day. A little bit cold up there now. I hope it likes it up there. That's it for now. Ta-ta. Over. Once again, we visit the 356 engine exploded view. This time, we left it alone overnight, so something new and exciting has grown while we were gone. This situation applies to those people who have 1968 model year 912s, ones that have the air injection pump. They have a funny left rear mount that goes between the third piece of the case and the engine. There's a fan belt cut out for the drive build for the smog pump that the 68 912s have. And consequently, because of this cutout they use to make the fan belt clear, a crack occurs. And when the crack occurs, you see It starts right at that right angle. That's a hell of a stress riser. It bisects the angle, and it will continue to go. Anyhow, the crack would continue to walk outwards there until it reaches outside area, and then it'll crack the rest of it. And we have another one down here that's been cracked like that. In fact, I'm willing to bet that pretty much every 68-912 known to man is going to start cracking like this or has already cracked. Let me give you a better view of this guy. There we go. Now that one that's cracked all the way through, and since there's nowhere to go there, it'll start on the other side next. And eventually what you get is one that's cracked like that. As you look up inside there, I'll zoom out a little bit more. There. You see the crack and how far it's gone. Be right back. Okay, here we have, if you guys have 68-912, anyone out there with 68-912, you better go out to your car and check out your left-hand rear engine mount. Connects between the third piece of the case and the bar that goes across the rear of the engine to support it. 1968 is the only year that had this particular cutout deal here. All the others have a solid rear, solid mount there. They're not that funny rectangular cutout or that V-shaped cutout. That's because only 68s have the dreaded smog pump, an air pump that injects cold air into the hot head, causes severe cracking in the 68-912 heads. This is the 68-912 rear mount where the fan belt or dry belt for that air pump must go through. That's why the notch. But the notch is a stress riser, and sure enough, at that lower left-hand corner, you can see a crack forming. And that crack will continue all the way out. And over here, if we go over here, we see that crack is continued at that right angle notch, a stress riser. It bisects the angle. Sure enough, it does. Goes all the way out, and all the stress is concentrated on the rest of the mount. And down here you can see a mount that's cracked almost all the way through, and I do have several cracked all the way through, too. So you have a 68-912 mount. Check the bottom of that cutout. There's two notches. They can crack from either notch, but usually this notch here is where they crack from. And they go all the way through the entire part of that rear mount, and you'll end up with your engine being supported by only the right-hand motor mount, which is not designed to handle that kind of load, will probably fail. If so, then your engine falls on the ground on the 68-912. So be extremely careful about that, you 68-912 owners. You can try welding it, or if you don't have the fan belt or dry belt for the smog pump working anymore, you can replace that left-hand mount with a regular any year but 68-912 mount and not have this problem ever again. Frankly, I think the latter is a better idea. And in conclusion here, we've left this thing overnight, this collection of parts, and what we found now is that when you do that, sometimes things reproduce in the darkness. Remember that fan that we had here in the beginning? Well, here it is now, mating with another one, making a cobra-like device ready to attack any innocent Porsche owner as he walks by. These things can happen if you don't pay attention to little details. And putting the fan on correctly without a big wobble and without bad teeth, not teeth, bad blades, can be a real serious problem. After all, you don't want to get bit by this cobra. This cobra always destroys the fan shroud, the oil cooler, and sometimes the cylinder heads by throwing hurricane velocity or tornado velocity fan blades. Okay, well, let's see what's arrived during the night here while the monster has slept. Let's zoom in on whatever might be new here. Oh, there's something that looks kind of new. Oh, another failed piston. Ah, but this one failed in a very strange way. Look at the wrist pin area and see how it's become oval-shaped, not circular. You know, the wrist pin retaining clip is still in place here, but the piston's been kind of eroded on both the bottom near the oil control ring and at the top near the compression rings. And you say, now, how could this possibly have happened? And you're right, it's kind of hard to visualize how this might have happened. But if we turn the piston around the other side, you may get a clue. So hang on, and I'll do that. Okay, now here I have the other side of the piston. You can see here the retaining ring, retaining clip, snap ring for the wrist pin actually came loose, no longer there. But ironically, what happened, the pieces from that snap ring bounced around inside the end of the wrist pin groove area, bead blasting or sandblasting the inside of the piston, as it were. But on the other side had the most damage. The pieces vibrated back and forth, went down the wrist pin, hollow wrist pin, of course, to the other side, and that's where they did most of their damage. In fact, if we take another close look at the other side, we will see that the wrist pin snap ring is still in place here, which from the standpoint of the particles bouncing back and forth acts like a dam and keeps the particles trapped between the outer part of that snap ring and the cylinder wall. So they vibrate back and forth. They're concentrated there to vibrate back and forth. They vibrate back and forth so that they can produce that hole. Will eventually eat its way through the rings, either top or bottom, to the top of the chamber. Or the pieces from all that operation, of course, going throughout your engine can do it no good. This happens when a snap ring comes out. This is, in fact, the wrong combination. It's a industrial, well, it's a Kolbenschmidt 85.5 millimeter big bore kit, the one that the NPR boys copied. And in fact, they did such a nice copy that the guy who put this together thought it was an NPR big bore kit, and that retaining ring is an NPR big bore kit circlip, or snap ring, internal snap ring, with the eyes to take it out, not the pliers type. Anyhow, this is a big bore kit snap ring from an NPR Japanese big bore kit used in a Kolbenschmidt big bore kit. And it didn't work too well. The grooves are a little bit different. The Kolbenschmidt require the wire type retainers, and the cross section of the hole a little bit different, enough that the snap ring, the big bore kit snap ring when used in this application, came out on the other side. The pieces from it diffused through the wrist pin to this side here where the retaining ring was still in place, acted like a shepherd to guide the pieces, keep them smashing into the piston, and caused more damage on this, quote, undamaged side than on the damaged side that lost the wrist pin retaining snap ring. Also, you can tell it's a Kolbenschmidt big bore kit by the fact that it has a long skirt. Unless the skirt is cut, this piston will not clear the counterbalance cranks of the SC912 or counterbalance Super 90. The big bore kit boys were smart enough to realize that, so they made one piston clear everything. So one NPR big bore kit piston fits pretty much everything, although you have to accommodate higher compression. That is, if it's too high a compression, you must shim the cylinder or enlarge the hole in the head to provide lower compression. Otherwise, you have way too high compression with a big bore kit. But here's an example of the factory, quote unquote, 85.5 millimeter Kolbenschmidt big bore kit when you use the wrong wrist pin retainer clips. You want to use the wire type for the Kolbenschmidt and the pliers or the I-type snap rings, internal snap rings, for the NPR big bore kit, because the grooves are different. I really have to show this valve again. This is an ATE 3043 non-sodium filled exhaust valve used on the AB normal Super 90 exhaust valve. This is a real ATE one. It was bent because they used the wrong retainer keepers on the valve stem, and they came off, and the valve fell inside, got whacked by the piston. But if you take a close-up look at this valve, you'll see that there's no cracks whatsoever. Though it's bent in an S shape like that, a special valve for going around corners, it is still not cracked or broken or anything. You try and do that with some other valve, by some other manufacturer. In fact, this should be a commercial for ATE. Their valves took this kind of abuse and beating but did not fail. Now, of course, there are some other valves here that did fail, like that one there. But still, I'm impressed by that ATE valve. That's why I like ATE valves and use them in pretty much every engine I build. For racing, sometimes you got to change them out to different valves like Datsun or something. But you can form some interesting structures when parts hit other parts, and you end up with these Picassos, these works of art. Actually, they're works of Murphy. But that is my favorite valve, I must admit. We all have our favorite failed parts here. So once again, as we bid a fond adieu, a fond farewell to the failed parts in the Maestro's 356 engine exploded view, if you have a failed part, something of this type, don't feel bad because many, many other people do. There are about 1,000 parts in the engine, all of which must function successfully for the rebuild to be truly successful. And there are many potential problems along the way. But don't forget, we did get to the moon, too. Okay, if you remember, we were discussing the little defect caused by the idiot putting the number 3 main bearing of the 1950 to 1963 AB normal super bearing on putting the oil hole on the dowel pin hole rather than the blind dowel pin hole. I was describing the incredible phenomenon of how that dowel pin gets shot into the crankshaft oil hole itself. And in one particularly rare event, well, I hope it's rare anyhow, the A crank and the early Bs up to about 1961 were not cross-drilled. They were drilled direct from the main bearing to the rod bearing. So the dowel pin, once it gets in the main bearing oil hole, can go all the way through on these cranks to the rod bearing. And this one did exactly that. And here you see a really nice groove worn in the middle of the rod bearing by the dowel pin that came from what was supposed to hold the number 3 main bearing in place. And by the way, now the dowel pin doesn't hold the number 3 main bearing in place. The number 3 main is free to spin if it wants to, and sometimes does. But this particular engine had the dowel pin go all the way through to the rod bearing and act like a machining tool on the middle of the rod bearing and machine that nice groove. It's about, a millimeter deep or so. Actually, a very nice oil distribution groove throughout the rod bearing, but one that was not intended. And of course, all the pieces in this machining operation went throughout the engine. But here is Murphy's machine shop at work in ways that you couldn't possibly conceive of. The thought that dowel pin that's stuck in that bearing could get all the way through to the rod bearing, you would dismiss as being impossible. But we don't say impossible around here after what we've seen. And we haven't seen it all. I'm sure there's more stuff out there that's weird like this. But this is a fine collection of weird parts and how not to do engine overhauls. If you do them right, they actually sometimes work out pretty well. If you do them wrong, the odds are extremely low they're going to work out pretty well. So let's see what else we have for you here in the hidden parts container. Okay, this is a rather interesting engine. This is the same engine that had the brass flywheel main bearing, the homemade main bearing. This guy over here, that was a brass flywheel main bearing homemade at the EBR2 machine shop, the Experimental Breeder Reactor 2 up in Idaho. This is a 2-piece case Porsche engine, about a 1953, used a VW bus. And out in the boonies of Idaho, I guess, back about 1963 or so, parts were not too readily available. So they had to make do with what they had. So here's some interesting effects of that same engine that had the brass flywheel main. If you look carefully on the connecting rod, as close as I can there on the connecting rod, down at the beam, you'll see what looks like weld material. And you're right, it is, on both sides of the rod. Rather than take material off the rod to balance them, this guy welded material onto the rod, right in the middle of the beam of the rod. Not necessarily a good thing to do. Also, you note the custom bearing from before. That was machined, the case was actually a line board to like a millimeter oversized, but they couldn't find bearings for it. So they couldn't find either rod nor main. So what they did was they took the rod and main bearings and put shims underneath it in the form of aluminum foil, about 5/1000 of an inch thick on both halves, so it makes for a bearing undersize. And they stuck it under both the rods and the main bearings. Now, maybe this will work in a Model T, but with like 10-to-1 compression and 356, it didn't work too well. As you see here, you see the remains of the aluminum. Anyhow, in Idaho, they didn't have spare parts available, and the case was a line board to millimeter over. They couldn't find those bearings for the Porsche engine, so they proceeded to make do with what they had around. They took bearings one size almost right, but one size under, and then used aluminum shim, aluminum foil underneath the bearings, both rods and mains. Now, this may work in a Model T or something, but in a Porsche with 10-to-1 or 9-to-1 compression or so, it's not a good idea. And that metal aluminum foil oozed out. You can see it in the rod bearing there, if I get the light right. oozed out, and you ended up with tremendous clearance in the bearings and bearing knock and rod knock and all kinds of things, low oil pressure, and they're bad enough the way they are. And this made it even worse. So you don't want to weld the connecting rod to balance it. You want to take mass off of it, not weld it on. You don't want to use foil under your bearings. That's not the right way of doing it. These are precision engines. You want to use the right bearing for your engine. An example of how you may, well, actually you can get a few thousand miles this way. If you have to get home, that's one way of doing it. But it's not the recommended way. So it's yet another one of the collection of the Maestro's broken parts on the engines he buys. One of many. 356 exploded view. This is a rather interesting device you don't see every day. This came in some industrial engines I got. They modified both the oil pump drive gear, and they added that little thing on top of the oil pump drive gear, which is a really clever design piece. That little curved loon-shaped thing on the top actually fits into the cam oil pump drive slot, and then they have, of course, a corresponding groove on the inside to fit in the tang of the oil pump drive gear. So this turns your oil pump drive gear with almost no wear of the camshaft and that oil pump slot wear, and the resulting wear of the tang of the oil pump drive gear seems like it ought to be a thing of the past. Good modification, I thought. It came with about a couple of rebuilt industrial engines that had this mod. Now, of course, the oil pump drive slot shaft has to be so much shorter to accommodate that intermediate drive piece. And there's only one other slight problem with this. On the engines I took it apart, it had this particular modification, which seemed like a good idea. There was tremendous wear of the engine inside, all kinds of pieces floating around in it. So maybe it isn't such a good idea. Well, look at that, will you? While we were gone, left this thing last night, it reproduced. The top rod there is, of course, a rather bent SPG roller bearing rod from the SPG roller bearing cranks, not unlike that SPG roller bearing crank that serves as my doorstop in the summertime. That's a good use for that, or a boat anchor is also good, too. But anyhow, the one on the top is an SPG roller bearing crank rod, and even they fail. The one next to it, of course, is a 912 rod, and that cracked right from the usual spot where the flat of the rod nut joins the connecting rod. That area there is a stress riser in the thinnest section, so they break there. They fatigue the stud on the other side, and once that stud breaks loose, then, of course, the whole rod comes off and goes through your case and makes that wonderful hold case effect, or the holy case effect. And then the one above there is a Hearth roller bearing crank from like a Super. One piece big end, that's the way you can tell roller bearing cranks. You know, it's missing a small end. So even the Hearth roller bearing crank is not immune to failure also. And then finally we have another one that has broken its rod. You can see where it cracked, right where that flat of the rod nut is located. You can see how it fatigued off the stud on the other half of the big end. And then as it went through the case, it took with it the wrist pin, and their small end is still the wrist pin of the piston, ripped from the piston, and then I used to pound the bejesus out of the case, so you end up with a destroyed case and crank, rod, and camshaft, and the whole bit. So you see, when you leave these things in a state, overnight, they sometimes do strange things. That's why I'm afraid to stay here late at night anymore with this engine here. And I always take a couple of pieces out so it's not complete, so it can't come to life and destroy all my other engines here. Well, once again, we get the view, 356 engine exploded view of all the possible exploded parts. Well, there's more that's possible, certainly, but a goodly selection of exploded and destroyed parts here. Maybe someday someone would like to put that on their TV show just to see what happens. Now, we have both kinds of problems here, failures caused by fatigue, old age and nature, and those caused by man. And, of course, the most disastrous ones are almost always those caused by man. Stupidity and ignorance are the two major reasons why the man-induced failures are the worst. Also, the fools. You can never make things foolproof because fools are so ingenious. They'll think of ways of putting that main bearing dowel pin on the oil hole you never thought of before. They'll think of all kinds of clever ways. And that's what you have to fight against, is the turkeys. There are a lot of turkeys out there, and they do things like this to engines. And if you get one, you have to make sure you exorcise the demons. Exorcise the demon. But there can be a lot of demons inside these things. Anyhow, I thought you'd like to see the collection of broken parts. I know it's horrible. Shouldn't be seen by children under about age 18 or so. And for many adults, you shouldn't see it either, but these things happen. Anyhow, if you want your engine done a little more properly than some of these have been, you may want to contact HCP Research, 320 Martin Avenue, Santa Clara, California. Area code 408-727-1864. Fax number is area code 408-727-0951. And we're on the internet. For email, use Maestro, all in small letters, Maestro, that's M-A-E-S-T-R-O, that's the @ sign, well.com, W-E-L-L.com. So all in small letters is M-A-E-S-T-R-O @well, W-E-L-L.com. Thank you for your attention. We hope you've enjoyed the show. Okay, once and for all, if you'd like to really know where the big bore kit piston design came from, here it is. Take a look at these two pistons here. They look identical, don't they? In fact, the oil return holes in the oil control ring are identical. The rings are identical as far as spacing goes, type, quantity. We'll turn these over. You can see the inside and the outside, and they come, to me, they look awfully identical. Let me pause it. Okay, and here's the top side of these guys. It's hard to tell which is which. The inside, well, this is actually the bottom side of these guys. And you're going to see they're quite identical. Rather interesting here. So let's see the top side. The side will tell a difference. Okay, here's the top side of these two pistons. The one on the left, you can perhaps see the arrow there. That's a big bore kit piston. That's a big bore kit piston with the arrow. The one on the right is a Kolbenschmidt piston. And you may not be able to make it out. It requires some directing of the light here. But Porsche factory pistons, Kolbenschmidt and Molly, use a picture of a crankshaft showing the flywheel end and then sometimes an arrow off the flywheel end. That's the side of the piston you want to put towards the flywheel. The big bore kit uses an arrow, like you see here. It's pretty obvious that it's an arrow. The Kolbenschmidt piston, as you can see, the arrow is not quite so obvious. So this one here is the Kolbenschmidt, and over here is the big bore kit. Now the big bore kit is Japanese, made by NPR, 86 millimeter diameter, and at one time available and cheap. The one on the right is a Kolbenschmidt, 85.5. Actually it says 85.47 there, and the piston, if you can read it, but I doubt if you can read that. It's a ½ millimeter smaller than the NPR 86 millimeter big bore kit, but that's what NPR used, copied. It's got the short skirt, the handle and counterbalance cranks. Let me compare the skirts. And basically identical piston dimensions and everything except the diameter. 85.5 millimeter oil return holes in the entire piston. The exhaust valve exhaust valve cutouts, the two eyebrows, one for putting it on the other way if you have to put it on the other side of the engine. Everything else is basically identical. You can really see where the big bore kit design came from the late model, the Kolbenschmidt big bore that had the short skirt to clear the counterbalance weights on the counterbalance cranks. One more characteristic explained, one more myth dispelled. Okay, here's a view inside the Kolbenschmidt piston. Maybe you can see that, but Kolbenschmidt has like a K and an S double stamped inside the piston there. If you get the right angle on it, maybe it's just about visible. That's their mark they cast into the piston when they make the piston. And over here is the big bore kit piston, which, as you can see, doesn't have that mark. But let's compare both of them now.